Everyone. This is V. Kavya, Assistant Professor, Department of Biomedical Engineering, Well-Tech Multitech, Dr. Rangarajan, Dr. Shakuntala Engineering College. Today I will be presenting an robotic prosthetic with sensory feedback, an emerging revolution in rehabilitation engineering and biomedical technology. This topic focuses on how modern robotic limbs are not only restoring the movement of amputees but also reintroducing a sense of touch, pressure, and even temperature. Through this presentation, I will explain the engineering concept behind prosthetic control, the role of biosignals, the sensors involved, how feedback is delivered to the user, and the challenges we face as researchers and engineers. By the end, you will understand how robotic prosthetics are emerging with human neurology to create almost nature limb function. Robotic prosthetic presents how the robots are working by using the next generation like artificial limbs. So this electronic actuators biomechanic and neural interfacings are used in an artificial limb. The traditional prosthetic devices could only restore basic mechanical movement, but they lack precision and provided no sensory response. Because of this, users had difficulty performing fine motor tasks such as picking up fragile objects, typing, or maintaining grip strength. Sensory feedback is essential because it allows the user to feel what the prosthetic is doing, making movement more intuitive, nature, and safe. Without feedback, prosthetic movement becomes guesswork. Therefore, integrating robotic intelligence and sensory input is necessary to improve functionality, comfort, and user satisfaction. These are several types of prosthetic based on how they are controlled. Body power prosthetics use cable and harness system, which is controlled by shoulder or chest movements. They are simple but limited. Myoelectric prosthetics are use surface EMG signals from residual muscles to control motors in the artificial limb, offering better precision. Hybrid prosthetic combines both body power and myoelectric control to increase functionality. The most advanced are neural integrated prosthetics, which connect directly to the user's nerves or brain, enabling more natural and intuitive movements. These systems can decode neural signals and provide sensory feedback through peripheral nerves, enabling near biological performance. Sensors from the foundation of both movement control and sensory feedback. EMG sensors detect muscle electrical activity and translate the electrical activity into command for the prosthetic. Force sensors such as FSRs measure how tightly the user is gripping an object, preventing accidental crushing of delicate items. Pressure sensor help provide tactile sensation when fingers through surface. Accelerometer and gyroscopes track limb orientation, angle, and motion, ensuring smooth and stable movement. Some advanced systems also use temperature sensor, vibration sensor, or optical sensor to detect environmental changes together. This sensor bring intelligence and awareness of prosthetic devices. Once the sensors collect all the data, the signal must go through processing to remove noise, extract pattern, and classify the intent movements. EMG signals are extremely weak and easily corrupted by motion artifacts, therefore, filtering using Butterworth or bandpass filter is essential. After cleaning, feature extraction algorithms such as RMS, MAB, or wavelet transform identifying meaningful muscle pattern. Machine learning models like SVM, random forest, or deep neural network interpret this pattern to determine if the user intend to flex grip or rotate the wrist. This processing must be fast, accurate, and adaptive to work in a real time. After the intention is decoded, the prosthetic must perform the motion through its actuators. Most robotic prosthetic use small electromechanical actuator or servo motors because they are lightweight, energy efficient, and precise. Some advanced limbs use tendon drive mechanism where artificial tendons mimic the movement of human muscles. Pneumatic actuators and soft robotic actuators are also used for more flexible and biomimic movements. The design challenge is to provide enough torque for strong grip while maintaining low weight for user comfort. Actuator control must synchronize with sensor feedback to create smooth and natural motion. Sensory feedback is the heart of next generation prosthetic. Verbotactile feedback uses small vibrating motors on the skin to indicate grip strength or object texture. Electrotactile feedback sends controlled electrical pulses to the skin or nerve to produce artificial sensations like touch or pressure. Mechanotactile feedback physically presses against the skin to stimulate the touch. In more advanced systems, feedback is delivered directly to nerves through implanted electrode, restoring near new natural feeling of touch. Sensory feedback allows user to control grip without looking and to interact with object with more confident, precise, and emotional connections. Neural interface represent the highest level of integration between machine and the human body. Peripheral nerve interfaces such as cut-off electrodes or regenerative electrodes attach to or grow around nerves, enabling two-way communication. They read neural signals for control and deliver electrical stimulation to provide sensation. Brain machine interfaces also still experimental decode signals directly from the motor cortex and offer extremely accurate control for people with high level amputation. However, challenges include long term stability, risk of infection, biocompatibility of electrodes, and complex signal decoding. Despite this, neural interface show promise as the future of prosthetic rehabilitation. To understand how this system works in a real life, let's look at two examples. The first is an upper limb robotic hand developed at Johns Hopkins APL, which uses EMG and neural implants to allow amputees to control each individual finger. Users report the ability to feel pressure and texture through sensory remapping. The second example is the Autobox Smart prosthetic leg, which uses gyroscope, accelerometer, and force sensors to help users walk naturally on uneven terrain. Both systems demonstrate how robotic biosensing and artificial intelligence are transforming prosthetic technology into something close to the natural limb function. Despite the progress, several challenges remain. EMG signals can be inconstant due to sweat, electrode placements, or muscle fatigue. Sensor noise and latency can reduce real time performance. Battery life is a major limitation as prosthetic must be lightweight yet powerful. Neural implant require complex surgery and carry risk. Prosthetic cost is extremely high, making them inaccessible for many patients. Additionally, ethical questions arise about emerging robotic and human biology, especially concerning privacy of neural data and the psychological impact on users. Overcoming these challenges will require interdisciplinary effort across engineering, medicine, AI, and ethics. The future of prosthetic is incredibly promising. Artificial intelligence will enable prosthetics that learn from the user's daily movement and adapt automatically. Soft robotics will make limb flexible, lightweight, and more similar to biological tissues. Fully neural integrated limbs may one day restore complete sensory perception, including touch, temperature, and pain. 3D printing may make prosthetic more customizable and affordable, integrated with wearable sensor, cloud data, augmented reality cloud provide advanced rehabilitation solutions. The long-term vision is to create prosthetic limbs that function indistinguishably from natural limbs in both movement and sensation. In conclusion, robotic prosthetic with sensory feedback are not just mechanical devices, they are part of a future where technology merges deeply with human physiology. By integrating sensors, advanced signal processing, actuation, and neural interfacing, modern prosthetic offer abilities improve control, independence, and quality of life. While challenges exist, continuous advancement in biomedical engineering, artificial intelligence, and neuroscience are pushing the boundary of what prosthetic can achieve. Thank you for your attention, and I hope this presentation has provided deep insight into how robotic prosthetic with sensory feedback are transforming healthcare and rehabilitation.